Okay, now we're talking about magnetic forces on current carrying wires. We'll review over our right-hand rules, and then we'll talk about what happens with them. Important thing to understand is current carrying wires create magnetic fields. So if you have current running through a wire, you're going to get a magnetic field around it. Now, our two magnetic force equations, FB is equal to QVB and FB is equal to ILB. They're actually the same equation. QVB is the one you use when you have a single charge, something in coulombs, and then of course ILB will be what you use when you have current moving in a wire. But they actually work out to be the same thing. Q times velocity is equal to I times L. Now, let's take a look at this and work our way through this. Let's look at wire 1 first. I have B going into the screen. What I want to find out is what is the force on that wire and what the direction of it is. And I'm going to use the right-hand rule to do that. Now, we know that B is going into the screen, so your fingers are going to need to go into the screen. Now, we're only looking at number 1 right here. We'll do number 2 in a second. So if I look at number 1, my fingers are going into the screen. My thumb is now going to be directed down the screen. So if your fingers are going down and your thumb is going to go down the screen and your fingers are going into the screen, then the force has to be that way. Remember, it's three-dimensional in nature. So we have that. Now let's take a look at wire number 2. Now again, I'm only talking about this wire right here. So put a piece of paper up and ignore the other one. So now my fingers are going to go into the screen. Then my thumb is going to go in the direction of the current. And remember, current is nothing more than a repetition of charges. So it's really the same right-hand rule. So if my fingers are going in and my thumb's pointing up, then the force is going to be that direction. Okay, one thing I left off of the equation is the sine of theta. I just wrote QVB and ILB. And the key thing to understand is, of the two wires shown, only one of them is going to feel a force. In order to feel a force, there has to be some part of B that's acting against the force. And it's maximum when it's perpendicular. So wire number 1 is going to feel a force. Wire number 2 is not going to feel a force. You can't do the right-hand rule with number 2. Your fingers don't work that way. So therefore, 1 is going to feel a force. This is the only one that feels a force. 2 is not going to feel a force. Now, let's figure out how to feel what that force is. Your fingers are going to go in the direction of B, so your fingers are going to point that way. And then your thumb is going to go down the screen. And if you do that, then your F is out of the page. No F on this one. Okay, now let's talk about the magnetic field around an isolated wire, and then we'll apply that to forces. So this is our second right-hand rule. Now what I'm going to do is I'm going to put my thumb in the direction of conventional current, which is positive to negative. Then my fingers are going to wrap around to show you B. Again, it's three-dimensional in nature, so therefore it's hard to draw really on a picture. The magnitude of B is equal to mu naught times I divided by 2 pi r. 2 pi r is really just the circumference. It's really nothing more than a constant times the current divided by the circumference of the circle. Eventually, when you add calculus to the mix, those of you that are going to go on in engineering, this actually becomes a little bit easier. The mu naught constant is 4 pi times 10 to the negative 7th Tesla times meters divided by amps. That's just to make the units work out. The nice thing about it, and the reason we leave it as 4 pi times 10 to the negative 7th, is you have 2 pi on the bottom, so it makes your math easier to leave it that way. That will give you the magnitude of B. Remember, it's inversely related to R. So if you double the distance, you'd have half of the magnitude of the B field. Now here's the sample problem. What is the strength of the B field 2 centimeters from a 15 amp wire. And you know what I'm going to do this time? I'm going to let you work it out. Show it to me on your notes. Okay, now let's look at what happens when we have a wire in a magnetic field and watch what happens. So in part A, I have, you see a north and a south pole of a magnet. So therefore, it kind of gives you an idea of what the three-dimensional nature is. In B, there's no current in the wire. If there's no current, there's no magnetic field. Remember, it's the interplay of the magnetic field caused by the wire and the magnetic field caused by the magnet that's going to cause it to move. Now, let's go to take a look at C and C only. Now, your fingers are going to go into the page because B is going to go into the page. Your thumb is going to go in the direction of conventional current flow, which they tell you is going up the page. So therefore, your force is acting that way, and that's why it bends that way. Now, let's take a look at D. Now what happens is my fingers are going to go into the page, but now my thumb is going down the page, so therefore F is going to be to the right. Remember, the right-hand rule works anytime I have a magnetic field and current moving or electric charges moving. Remember, current is nothing more than electric charges moving, so it's the same concept. Now, two wires going in the same direction is a little more complicated, at least now you think about it. I'm going to call this wire 1 and I'm going to call this wire 2. And what I'm going to do is I'm going to look at wire 1 first. If I look at wire 1 first, I put my thumb in the direction of conventional current and wrap my finger. So on this side, it's going out of the page. This side, it's going into the page. Remember, out we usually use as dots. In we usually use as X's. So let's extend that all the way over to here. And now let's take a look at what happens with wire 2. So now I'm only going to deal with wire 2 here. Now, your fingers are directed into the page, and your thumb is coming up the screen, so therefore the F is going to be that way. Now, if we treat the other wire the same way, so now let's look at wire 1. And let me change. I'll go to, let's go to blue. So black represents the B field from wire 1. I'm going to use blue to represent the magnetic field from wire 2. Okay. So now, what happens with wire 2, I'll tell you what, let's go to a completely different color. Let's go to pink. Okay, so now what's going to happen now is I'm now looking at wire 2. When I look at wire 2 and I grab it, and again I wrap my fingers, it's going to be in on this side and out on this side. So in, remember, as we use X's. Okay, and then over here, it's going to be coming out, so I'm going to use dots. So if my fingers are pointing out of the screen and my thumb is pointing up the screen, then the force is going that way. Those two are going to attract because the forces are going together. Now if we look at two wires going in opposite directions, so now we're going to have opposite directions. Now, again, I'm going to go to wire 1, call that wire 2. Let's look at what happens from wire 1. If I grab wire 1 with my hand, it's going to be in on this side and out on this side. So it's in that I'm really worried about. So I'm going to draw the X's, and I'm going to continue the X's all the way till they get to this point. Because what's going to happen now is my fingers are going into the page. Now I'm only looking at wire 2. My fingers are going in where wire 2 is. My thumb is going down, so therefore the force is going to be that direction. Now, if you go through the same thought process going back the other way, you're going to end up finding out that this force is going this way. Try and prove it to yourself. Since those forces are opposing each other, these wires are going to repel. And I have a way I'll show it to you in class. Another way to visualize it is to look at the fields that are created by the current carrying wires. And by the way, the typo was not me. I just want to make sure you understand that. So let's look when the currents are going in the same direction. If the currents are going in the same direction, I get magnetic fields that are wrapping around like this. Over here, I get magnetic fields that are also wrapping around like this. So what I have here is these fields are attracted to each other. If I look at this one over here, now what's going to happen is my fields are pointing in opposite directions. Let me see if I can make that picture a little bit bigger. Let me go select. So what's going to happen now is they're going in opposite directions. So therefore, they're going to repel. So in this case, repel. The other case, attract. Now, let me show it to you from a different angle, which may make it a little bit easier to visualize. What we have near is an end view. And if you have an end view, what happens is you may be able to see it easier here. What's going to happen now is the wires that are, the B fields that are wrapping around on the top diagram. This one is going in, this one is coming out. So those are going to, if you do the right-hand rule, when you go in, it's going to wrap around that way. When it's come out, it's going to wrap around that way. What's going to happen is these are going to repel away from each other. If I extend these circles out here, it may actually be easier for you to see. Let's say if you extend that circle that way, that's the circle from this one over here. And now what's going to happen now is your B is directed up, a tangent at this point right here. At this point right here, B is going to be directed up. It's tangent to the circle. And then if my thumb goes into the screen, that's what leaves this force going that direction. So it may be easier to visualize from an end point of view. You can also look at the end point of view for an attractive force, and you can see that they're going to attract each other. You can do the same thing we just did if you want. You can go, okay, let's start with this wire and look at the magnetic field from that. That's these circles. What I want to do is extend these circles out to here. If I extend these circles out to here, that means the B field right here is pointing up from this. So I can say B is pointing up. If B points up, that means my fingers need to point up. And if my fingers point up and my thumb is pointing out of the screen, that's going to account for the force acting that way. You can repeat it for the other one and see that when they're going in the same direction, they're going to attract. When they're going in opposite directions, they're going to repel. Okay, let's focus here on wire 2. And look what happens with the math involved in this. First of all, we have to figure out what is the B field at 2 based on 1. So what we're trying to do is figure out, change that color, the B field at 2 from 1 is equal to mu naught I1 divided by 2 pi times r. And we can just leave it like that. Now, the next thing I want to figure out is the force from 2. Well, the force on 2 is going to equal I2 times delta L. And L would be the length that's in the field times B, ILB. So now, let's combine those two equations, and I'm going to get force, and I'm going to go ahead and divide by delta L, because I usually don't have to fool with that. What I'm talking about is the force per unit length. And when I put those together, all I'm simply going to do is take I2 times B2. So when I do I2 times B2, what I get is mu naught I1 I2 divided by 2 pi r. Now, that equation is not going to be given to you, but what it does is it allows you to calculate the force if I have two current carrying wires. And I would simply take its mu naught, which is again a constant, times the product of the two currents divided by the 2 pi times the distance between the currents. If you need that equation, and I don't know that you will, if you need that equation, just derive it when you need it. Realize that force is equal to I times L times B. Use the other formula to calculate B. Hope this helped.